What's up? We're talking about the second derivative test, which is another application of the second derivative. And so this is another test for extrema. So like the first derivative test, it tells us if we have a minimum or a maximum. And so let's take a look at what we have here. So we're defining if f prime is 0, so meaning we have a critical point, okay, and the second derivative is greater than 0, meaning we're concave up. Okay, then f of c is a relative minimum. Right, so that means that we have a critical point at sort of a valley here, meaning we have a minimum. So same thing, if we have a critical point, and this time my second derivative is negative, meaning we're concave down, that means we have a relative maximum. All right, so there's a lot of stuff to remember here, don't get confused. Okay, so we're using critical points to determine where we have extrema. So for the first and second derivative test, we're using critical points. And then we're either plugging it into the first or the second derivative, depending on which test we're using. And sometimes it's easier to use one or the other, and sometimes you can only use one or the other. So that's why we have these multiple tests. Okay, in our first example, we're asked to use the second derivative test to find the relative extrema of this function. It says if possible here because sometimes the second derivative test does fail. Sometimes it tells us nothing, but anytime that I would ask you to use it, it should work. But just keep in mind sometimes it won't work. So let's find our first derivative. All right, so we'll get negative 15x to the fourth plus 15x squared. All right, and we still need to find our critical points here. So let's factor out a negative 15x squared. So we'll get x squared minus 1 is equal to 0. That means that I have critical numbers at 0 and then plus or minus 1. Okay, so now let's take the second derivative. And so we'll end up with negative 60x to the third plus 30x. All right, and this time I'm plugging in my critical points. So instead of making a number line, I'm just plugging in what I know. So I need to find f double prime of 1, f double prime of negative 1, and f double prime of 0. Okay, I'm plugging them into my second derivative. Okay, so first of all, if I plug in the 1, I'll get negative 30, which is obviously less than 0, which means that my function at this point is concave down. This tells me that I have a relative max at x equals 1. All right, so 1 was our critical point, and remember that's where we're eligible for extrema. And then by plugging it into my second derivative, I found that at this critical point, my function is concave down because I have a hill here. And so my conclusion is that I have a relative maximum. Now let's talk about justification. Right, so because f prime is 0 and f double prime is negative. Right, so that would be my justification here for the second derivative test. F prime is 0, f double prime is negative. All right, if we plug in negative 1, we get positive 30, which is obviously greater than 0, meaning we're concave up. So this tells me that I have a relative minimum at x equals negative 1. And again, my justification, because f prime is 0 and f double prime is positive. Okay, now here's where the test can go wrong. So if I plug in 0, I just get 0. Okay, this tells me nothing because I have to know if it's either positive or negative to determine concavity. If it's 0, that tells me no information, so my second derivative test fails. Okay, so I don't know if it's a max or a min or if nothing's happening there. I have no idea. All I know is that my test failed. Okay, so that answers the question. All right, let's move on. So here we're given some function values and then something that looks kind of complicated. And it's asking me if g has a local maximum or a local minimum at x equals 3. Okay, so this is a situation where it's impossible to use the first derivative test because I do not have a function to plug values into. Like I can't make a number line. So let's take the derivative of g. So here I have a product of two functions, so let's use product rule. All right, so first my derivative will be 2x plus, and then x squared minus 9, and then times the derivative right here. So 2f prime of x plus 5 double prime, 5f double prime of x. Alright, this isn't going to matter as much. So I'm wanting to evaluate at 3. So let's plug in 3 and see what happens. Right, so I guess I'm assuming here that 3 is my critical number, so I'm using the second derivative test and plugging 3 into the second derivative. So I'll end up with 6 times 2f of 3 plus 5f prime of 3 plus, and then 3 squared is 9, so 9 minus 9 is 0, so all of this will end up being 0. Alright, so they told me that f of 3 is negative 4, and they told me that f prime of 3 is 1. So this means I got negative 8, plus 5 is negative 3, times 6 is negative 18. Right, so negative 18 is definitely less than 0, which means that I'm concave down, meaning that g has a local maximum at x equals 3. So I can say that g has a local max at x equals 3, and again my justification is because, and here I'm assuming that 3 is my critical number, so I can say g prime of 3 is 0. Okay, that's the assumption that I'm making. And g double prime of 3 is less than 0. Alright, so that's it for these notes. I'll see you all later.